Assalamualaikum and selamat sejahtera. In the last video, I have explained the circuit topology and the principal operation of single-phase uncontrolled rectifiers. As the continuity of those topics, I will teach you how to sketch voltage and current waveforms of the rectifiers. These waveforms are essential to verify the performance or the operation of the rectifiers in converting AC power to DC power. You can sketch this waveform using voltage and current equations obtained from the equivalent circuits of the rectifiers. To get voltage and current equations, we need to analyze the equivalent circuits of the rectifiers using Kirchhoff's law or Ohm's law. Firstly, let's start with a single-phase uncontrolled half-wave rectifier with a resistive load. As we discussed in the last video, we know now that the operating condition of the rectifier's diode depends on the AC supply voltage waveform. Based on the positive and negative half cycle of the AC supply voltage, the rectifier has two equivalent circuits. The diode is in forward bias when the omega t value, which is the angle of the AC source, is in between 0 to pi. Based on the ideal turn-on characteristics, the diode will act as a short circuit to conduct current with zero voltage drop. Hence, we can write the first equation of the circuit, which is the voltage across the diode equals to 0. Next, by observing the circuit, we can see that the resistive load is connected in parallel with the AC source. Because of that, we can write the second equation, which is the output voltage across the load is equal to the supply voltage. Lastly, we can write the current equation by applying the Ohm's law. When the omega t value is in between pi to 2 pi, the diode is in reverse bias. In this condition, the diode will act as an open circuit to stop the current conduction. Thus, the current equation is equal to 0. Furthermore, since there is no current flowing in the circuit, therefore, the output voltage is also equal to 0. Lastly, by applying KVL, we can obtain the voltage equation of the diode. Based on this equation, it varies the turn-off characteristics of an ideal diode, which is the diode will stop current conduction by blocking a large reverse voltage. Based on the operating condition of diodes, a single-phase uncontrolled full-wave rectifier with a resistive load also has two equivalent circuits. First, when diode D1 and D2 are in forward bias. Hence, automatically, the voltage value of both diodes is 0. Next, as similar to the half-wave rectifier, we can see that the resistive load is connected in parallel with the AC source. Thus, the output voltage is equal to the supply voltage. Then, as usual, we can apply Ohm's law to obtain the output current equation and KCL to obtain supply current equation. The KCL is applied at this point. Lastly, we can obtain the voltage across D3 and D4 by applying Kirchhoff's law or KVL inside this loop. The second equivalent circuit is obtained when diode D3 and D4 are in forward bias. In this condition, both diodes act as a short circuit with zero voltage. Next, let us look at the connection between the resistive load and the AC source. Although both components are connected in parallel, however, their voltage polarity is opposite to each other. Hence, the output voltage is equal to the negative supply voltage. Later, we applied Ohm's law and KCL to obtain the output current and the supply current equation. And KVL is applied on this loop to obtain the voltage across D1 and D2. Finally, now we have a complete voltage and current equations for the half wave and full wave rectifiers. Before we sketch the waveforms, I want you to give your attention to the range of the omega t value. The first and the second ranges are referring to the positive and negative half cycles of the AC voltage respectively. Usually when I sketch the waveforms, I prefer to use the VI characteristics of an ideal diode during forward bias and reverse bias as my reference. During on state, the diode should conduct current with zero voltage drop. Meanwhile, during off state, the diode must stop current conduction by blocking reverse voltage. Based on these characteristics, I will rearrange all the voltage and current equations. I will start with the current equations, the diode voltage equations, and lastly, the output voltage equations. Next, we use the equations to identify the shape of both voltage and current waveforms. According to the current equation in 2a, we can see that the current wave shape is similar to the supply voltage waveform. However, based on Vs divided to R, we know that the amplitude of the current waveform is lower than the amplitude of the supply voltage. On the other hand, based on equation 1a and 3b, we can see that the output and diode voltage waveforms have the same shape and amplitude as the supply voltage waveform. As a summary, the wave shape of the current, output voltage, and diode voltage is following the supply voltage waveform. Now, we need to sketch three sets of axes. The top axis is focusing on the voltage and current waveforms at the supply or AC side. Meanwhile, the middle axis is concentrating on the voltage and current waveforms at the output or the DC side. Lastly, the bottom axis is focusing on the voltage and current waveforms of the diode. Since all parameters are related to the supply voltage, hence we start the sketch by drawing the supply voltage waveform using its general equation. Based on the equation, the shape of the AC supply is a sinusoidal wave shape with an amplitude of Vm. Thus, according to the previous discussion, we now know that the current, output voltage, and diode voltage in these equations are also sinusoidal. For the next step, we need to sketch two vertical lines to separate the positive and negative half cycles of the supply voltage waveform. As discussed before, only during the positive half cycle of the supply voltage, diode D is in forward bias. Thus, we can use an arrow to label the range of the forward bias on the graph. So, we will know that the diode will conduct current only in this range. This range, which is in between 0 to pi, is known as the conduction range of the diode. From the range, we can calculate the conduction angle of the diode by subtracting pi with 0. As a result, the conduction angle of diode D is pi, or 180 degree conduction angle. This conduction angle indicates that the diode is only conducting current for 180 degrees or half of a complete cycle of the rectifier operation. Lastly, we will sketch the remaining waveforms using these equations. As discussed, we will start with the current waveform. Since the current equations shown in 2a and 2b are referring to the output current, hence, we will sketch the waveform on the middle axis. Next, on the bottom axis, we sketch the diode voltage waveform. Finally, on the middle axis again, we sketch the output voltage waveform. To complete the current waveform of the AC source and the diode, we need to refer to the single-phase half-wave rectifier circuit. Based on the circuit, we can see that there is only one current pathway existed. Because of that, this output current is also the supply current and the diode current. By referring to the diode current, we can verify that diode D only conducts current for half cycle or 180 degrees only. Based on the complete waveforms, we can see that diode D can conduct current with 0 voltage drop during the positive half cycle of the supply voltage. Furthermore, since current can flow to the load, thus we also have the output voltage waveform. In opposite, during the negative half cycle of the supply voltage, diode D will stop the current conduction by blocking a large reverse voltage. Since there is no current flowing to the load, therefore output voltage equal to 0. Lastly, the peak amplitude of the diode voltage waveform, which is negative Vm, is known as the peak inverse voltage or PIV. It's referring to the maximum reverse voltage a diode can block during reverse bias. Next, when we compare the voltage waveforms on the top and middle axis, we can see that the voltage waveform on the top axis is AC voltage, while in the middle axis, it is DC voltage. Hence, these waveforms have verified that the rectifier has converted the AC voltage to DC voltage. However, when we look at the current waveforms on both axes, we can see that both currents are DC. Based on that, we can state that the operation of the single-phase uncontrolled half-wave rectifier with a resistive load has caused the AC source to supply DC current. Therefore, this rectifier is not suitable to be applied in a real application. Before I end this video, I will guide you on how to sketch voltage and current waveforms of a single-phase uncontrolled full-wave bridge rectifier with a resistive load. We will use these equations as our reference. To see the relationship between the full wave and the half wave rectifiers, let's study their voltage and current equations. Here we can see the similarity between the output voltage and output current equations of both rectifiers during the positive half cycle of the supply voltage. According to the equations, the output voltage and output current waveforms of both rectifiers are following the shape of the supply voltage waveform. It is because diode D in the half wave and diode D1 and D2 in the full wave rectifiers are in forward bias. Nevertheless, during the negative half cycle of the supply voltage, diode D is in reverse bias. As a result, the output voltage and output current equations are equal to 0. On the other hand, in the full wave rectifier, diode D3 and D4 are in forward bias. Hence, the current is still flowing to the load. Based on the output voltage and output current equation, we can see that the wave shape of both parameters are following the shape of the supply voltage. However, the equations show that the polarity of these parameters are in opposite to the polarity of the supply voltage waveform. While keeping this concept in mind, we will start to sketch voltage and current waveforms of the rectifier. When you want to start the drawing, first sketch the axis and the supply voltage waveform. Then, label the conduction range of all diodes. Please remember that the conduction range is referring to the omega T value in which the diode is conducting current. Based on the labels, we can see that each pair of diodes has a different conduction range. For D1 and D2, it is in between 0 and pi of the omega T value, and for D3 and D4, it is in between pi to 2 pi of the omega T value. Although both diode pairs have different conduction range, the conduction angle of each diode is similar, which is pi or 180 degrees. Now, let's continue the drawing. Based on equation 2a and 2b, sketch the output current waveform on the middle axis. Next, draw the diode voltage waveforms on the bottom axis based on equation 3a and 3b for diode D1 and D2 and equation 4a and 4b for diode D3 and D4. Later, sketch the output voltage waveform on the middle axis. Lastly, based on equation 5a and 5b we can sketch the supply current waveform on the top axis. Based on equation 5a, we can see that the wave shape of the supply current waveform is similar to the output current waveform. However, according to equation 5b, the supply current waveform is opposite to the output current waveform. Thus, the wave shape of the supply current is sinusoidal. From the complete waveforms, we can see that the voltage and current waveforms on the top axis are AC, while the voltage and current waveforms on the middle axis are DC. These waveforms show that the power conversion performed by the full wave rectifier is not affecting the AC supply current as the half wave rectifier operation. Now, I will apply KCL on the rectifier circuit to obtain the relationship between the output current and the diode currents. Current 1,2 is referring to the current that flow through D1 and D2, and current 3,4 is referring to the current that flow through D3 and D4. If we apply KCL at this point, then the output current is equal to I12 plus I34. This equation shows that the output current waveform is a combination of current D1 and D2 during positive half cycle of the AC supply plus current D3 and D4 during the negative half cycle of the AC supply voltage. Therefore, we can sketch current I12 and current I34 as follows. Based on the waveforms of the diode's current, we can see that the output current will commute from D1 and D2 to D3 and D4 when the positive half cycle of the AC supply voltage change to negative half cycle. This current commutation happens when omega t is equal to pi. Therefore, we can call this vertical line as a commutation line. If we consider the second cycle of all waveforms on the positive and negative sides of the y-axis, then these two vertical lines are also commutation lines. Based on the waveform, we can see that the current commutation occurs instantly when the half cycle of the supply voltage waveform changes in polarity. Lastly, when we compare voltage and current waveforms of the bridge and split supply rectifiers, we can see that both rectifiers exhibit the same voltage and current waveforms except the diode voltage waveforms. According to the diode voltage waveforms, we can see that the PIV of the split supply rectifiers diode is 2 times higher than the bridge rectifier. Therefore, we need to use diodes with a higher voltage rating for the split supply rectifier than the bridge rectifier. Because of that, a single-phase, uncontrolled, full-wave bridge rectifier is more commonly found in real applications. That's all for today. I will see you in the next video.